Hello everyone and welcome to this video. We will continue where we left off last time. We'll do a few more examples and I'll explain a couple more things for this type of instructions. So if you remember last time we hand assembled the instruction add R1 hashtag 1, which is essentially add 1 to R1 and store the results back into R1. Another way to look at this is increment R1 by 1. And then we got the hex value to be E2811001. Now, what I'm going to do is I'm going to do another instruction, and I'll use the add just to show you how this works without the immediate value. So let's do an add. Let's do R2, R3. Doesn't matter really, uppercase or lowercase. Let's do R2 plus R3. Or R2 equals R3 plus R5, for instance. In this case, I'm going to also change the condition here so that we can see how it works if it's not always. Let's say add NE. So add if not equal R3 to R5, store the results into R2. So we will start with the condition. Let me remove those bits first. So the first 4 bits from the left is the condition. This is NE. I have that condition NE. And when we look at the table, NE is 0001. And if you're wondering what table I'm talking about, I am referring to this one right here. So you will see the condition NE has the value of 0001. So going back to my hand assembly here, I'll put 0001 and then I have the 2 00s here, and then in this case I'm not using an immediate value. I'm actually adding 2 registers to each other, storing the result in the third one, so the immediate value bit is 0. And then the opcode for the add instruction is 0100. Where am I getting that number? From this table. So here you'll see the add instruction is 0100. So I go back and type that in, 0100. Then the S modifier is not being used here, so that's a 0. The first operand is R3, and 3 in binary is 0011. The destination register is R2, so 0010. And then the second operand is my R5, and for that I have 0101, and then I have 1 2 3 4 5 6 7 8, and then altogether they'll be my 12 bits, right? So 12 bits, bits number 0 up to 11. Now you can, if this was done let's say on a whiteboard or so, it would be easier to group them, but here I'm going to just like modify the spaces a little bit so I can actually look at them in groups of 4. It will be easier to do or to get the hex value that way. Like that. Okay, so if I look at this value, so 1 is essentially just 1, and then these 4 bits are 0. This is 8. This is 3. This is 2. 0. 0. 5. Now let's double check this in the assembler. Here I have the instruction written add NE R2, R3, R5, which is what I had assembled a second ago. If I look at the disassembly, I'll see the value of that instruction in hex, or the code of that instruction in hex is 10832005, which is similar to what I have done myself, 10832005. Let's do one more instruction and switch it up a little bit. Let's do a subtract and an S to modify the CPSR. And let's subtract the value of 1024 from R1. And I want to show you something here, so bear with me for a second. I want to show you how this number affects what the first 12 bits 0 to 11 in this instruction. So Let's start with this hand assembly. So the condition here is implicit AL. This instruction will always execute. So that's 1110, followed by hard-coded 2 zeros, followed by the immediate bit or the immediate field. I'm using an immediate value, so that will be 1. And then the opcode for the subtract is 0010. And then I am using the S modifier after this instruction. So I have the sub S. So the modifier S is actually in the instruction. Now the first operand for this instruction is R1. I'm essentially subtracting a number from R1 and storing it back into R1, and 1 in binary is just 1. The destination register is also register 1. Now the question is, how do I implement 1024? Okay, so for the second operand, if I want to encode 1024, I'm just going to write 1024 here using 12 bits. It will be simply 2 to the power of 10. But that's not how it works, actually. I have to leverage, if you guys remember from one of the immediate value lecture that we had here, I'm going to just do this. I have 4 bits for the rotation amount, and I have 8-bit or 8-bit immediate value. Right, so the 12 bits are actually used to indicate a rotation amount and an 8-bit immediate value. So the question becomes, what value do I use, or how do I arrange these bits such that if I start with the number, with the immediate value, if I start with this number right here, and I rotate it so many times, I have to figure this number to get 1024. Without spending too much time here, actually, you can refer back to one of the lectures that I have. You can refer to that one, actually. We talked about generating immediate values for instructions using these 12 bits. We talked about how this value is multiplied by 2. So this enables the system to generate a value that is a multiple of 2 to the power of 32. Because if you have 4 bits, the most you can do is 2 to the power of, 2 to the power of 3, essentially, or 15, multiplied by 2, so you can actually scale that much. So you will find out that if you put the value 1 here, so 0, 0, 0, followed by another 4 zeros. So if you put the value 1 and you rotate this 1 22 times, you rotate right 22 times, you will get your 1024. So since I'm rotating 22 times, and this number is half of that, so half of 22 is B, and B in binary is 1011. So my 12 bits here will be 1011, 0000, 0001. Again, if you want to review how I'm getting this value exactly, please watch the video in which I speak about or go over the immediate value generation. And if you still have comments or if you still have questions, write me a comment and I'll try to address that. So I'm going to remove this right now and go back to continuing this example. All right, so here we have E. We are grouping those in terms of 4. And then 0010, that's a 2. Let me put a space here. It's easier to see that way. And then bring that one closer. And then I'm kind of done. So here, this is a 5. This is a 1. This is a 1. This is a B. 0, 1. So S or subtract S, R1 hashtag 1024 translates into E251 1B01. Let's see that in the assembler. So here I have the instruction sub S, R1, R1, 1024, essentially subtract 1024 from R1, store the results back into R1. The value we get, the hex value for that instruction is E2511B01, which is what we got when we did it manually. So that's it for this video. In the next video, I will go over manual assembly of branching instructions. And the one after that, or the same one, we'll do the load store multiple manual assembly. Thank you for watching.